Good evening students. Today we will try to discuss about application specific integrated circuit design flow, that is Asic design flow. Asic design flow. So now before discussing this flow we will try to understand that you are all IC designers. Okay, so you are getting some specification from the customer. Okay, the specification is, say suppose full ladder. You have to design a full ladder. The customer is saying that design a full ladder for the frequency of 2 GHz, 5 GHz, whatever it is, right? The specification is the first input for any design. Specification is the first input for any design. Okay, the specification may be power or area, chip area, or maybe the speed. Okay, so considering this specification, there will be a top level guy in your company, IC design company, that is called top level manager. Okay, so the top level manager decides the micro architecture for the specification whatever is given by the customer. Customer gives the specification, so based on the specification, so top level guy decides the micro architecture, sample architecture, right? Sample architecture. So that's sample architecture represents what? There is a full ladder. Full ladder requires one half adder and another half adder. These are blocks. Block number 1, block number 2, right? So I need to have some more standard cells like RA, right? So this model block may require this much of area, this much of power, right? Some estimation this fellow is doing, again he is communicating the customer saying that, so this chip may go for say 2 crores, 3 crores, right? So they are fixing the cost as well as the design details. Once the customer is happy with the micro architecture, whatever is developed by the top level guy, he is saying green signal, saying that start, right? So once the micro architecture is finalized with the customer, we have to go for RTL design, register transfer level design. So this registered, suppose if you are going for a microprocessor consists of a lot of blocks, ALUs, right? FPU, normal arithmetic units, inbuilt memories, cache memories, right? So each and every module is given to different guys or different low level engineers. So he may be assigning some modules to the lower level project leads. Project leads assigns the work to the lower level engineers, right? So the work is divided into different groups. Block by block is assigned to the different groups. So different groups, they are making their own individual RTL, that is called the first stage of our technology independent work. Technology independent work. Okay. So once the RTL is designed, we need to verify the functionality, whether the RTL whatever you designed is working fine or not, right? So for that we need to go for simulation. So make sure that while going for ASIC design, you are making synthesizable RTL. There are 2 versions of RTL, one is non-synthesizable, the other one is synthesizable, right? So you please make sure that you are writing RTL synthesizable and go simulate. Okay. So once the functionality is verified, yes, applying just test vectors, check whether all your functionality is correct. Once the simulation is verified, we need to go for the process called synthesis. So up to this, your design is called as technology independent design. Up to this simulation, your design is called as technology independent design. The moment you take the design into the synthesis, this is called as technology dependent. If the output, whatever you are getting from the synthesis, is called technology dependent design. So what is happening in synthesis? Synthesis is a 3-stage process. So translation, optimization, mapping. These 3 processes combinedly represented as synthesis. translation, optimization and mapping into the particular technology. If you are going for 32 or 45 or 15, whatever the technology, right? So that specific technology library, considering the technology library, you have to convert the design into the specific node design, 45 or 32, whatever, right? So that is called synthesis. So once synthesis is over, we need to generate two different files from the synthesis. One is called gate level Verilog netlist. So after this, your design is .b. The file whatever is available is .b. Once you cross the stage synthesis, the file whatever you are having is BG, gate level Verilog netlist. Okay. So apart from that, we need to specify the constraint for our design, that is called synapsis design constraint. Okay. So what is your input delay? What is your output delay? What is your clock period? Whether your design is having any multi-cycle path, is there any false path in your design? What is your latency, clock uncertainty, right? All these specifications you have to mention in your synapsis design constraints for your design. Design to design, this SDC will vary. Okay, so we have to generate these two files from the synthesis. Once the synthesis is over, gate level Verilog netlist is ready, .SDC is ready, right? Then we need to go to the next stage. That stage is called design for testability. Next stage is called design for testability. That is called DFT. In DFT, we have to measure the controllability and observability of our design. Right? How far our design is achievable. That is in terms of error rate. That is what percentage of the design we can just go and cover. Right? So that kind of measures we are doing in the DFT. Once DFT is finished, then we have to generate the file called ATPG. From the DFT, we have to generate the file called .ATPG, automated test pattern generated file. Right? So BG, gate level Verilog netlist, .SDC from the synthesis, .ATPG from the DFT, design for testability, right? So from simulation to DFT, we need to migrate from 3 to 4 tools. Only one EDA tool is not sufficient to cover all these issues. So in simulation, we have to do it with different tools. Synthesis, we have to do it with different tools, right? So industry standard sign-off tools for synthesis is design compiler from the Synapsis. Okay. So for DFT, you can go for encounter test, that is from the Cadence. Okay. Considering all these tools, we have to complete the process. Up to this, you can call your design as front-end Asic design. Front-end Asic design. Up to this. Okay. This is not the end. Your Asic design is divided into three varieties. One is front-end design, other one is back-end design, third one is fabrication. Okay. So now the first one is finished, that is front-end design is over. So once front-end design is over, so we need to go for back-end design. So back-end design, any design flow or any design with different EDA tools requires some data preparation. If you are doing any work with EDA tool, so minimum data preparation is required. So let me assume you are going for SOC encounter, that is for backend. That is place and route tool, P&R tools. Okay. So if you are now, till now we finished Synapse, that is synthesis, we are ready with gate level Verilog netlist, we are ready with Synapsis design constraints, right? So that is the first data required for us. So before doing the work, that is called P&R, we have to prepare the data. Data preparation. Okay. So what data we need to have before going for the backend? So first input is gate level Verilog netlist, that is generated from the either design compiler or RTL compiler, whatever the tool you want, you use. Okay. Then same way you please obtain Synapsis design constraints .SDC. That is also generated by the synthesis tool. You have to specify the constraints. Based on the constraints, the tool will give you SDC. Okay. So apart from that, we need to have lib, that is library files towards particular node. So if you are working for 45, we need to have 45 lib. If you are working for 20, we need to have 20 nanometer library. So library, we have three versions of library. One is slow.lib, other one is typical.lib, other one is fast.lib. That is to confirm the yield or to improve the yield in the later stage or in the fabrication stage. We are designing or we are just conforming with slow.lib, typical.lib, fast.lib. These libs are generated with different PVTs. Different PVTs, process, voltage and temperature, right? With the different PVTs, we are just making each and every lib will have same contents, same components. If you have slow lib will have a number of components. Fast will have a number of components, right? But components are same, but PVTs are different. Okay? So considering all this, so if you are going for a backend, you can either go for slow or fast as a setup, or you can go for only typical. So take two different corners, 16 corners, slow, fast. Load the libraries. Okay. So third input required is what? .lib. That is either slow to fast or typical. If you have only typical, that is also enough. If you have only slow to fast as well, that is also okay. So third input is what? .lib. Apart from that, we need to have one more information that is called length. Library exchange format. So this length contains metal information, via information, right? Height of the cell, pitch of the cell, poly width, everything. All technology related information will be there in the length. That is also another input for us. So we need to have .vg, we need to have .sdc, .lib with three different PVTs, and .left, that is technology information, right? So apart from that, so your design will be having some IOs. If you have a full ladder will be having three ins, A in, B, C, right? This is nothing but input cells or input pairs, right? And full ladder is having two outputs. One is called sum, other one is called carry. So this is called output pair. So in each and every design, we need to have some inouts, right? So that IO file is also required for us. That is also another input for the backend. So we need to have input output file, that is what is inouts of your design, what is SDC, constraints related to the design, gate level, Verilog netlist, optimized Verilog netlist, then left, right? So this is the minimum requirement we need to have before entering into the backend. Okay. Now, let me assume I have all the details with me. That is left, VG, SDC, .lib, .io, everything is there. Then the very first task in the B&RS, I need to go for floor plan. Before going for the floor plan, we need to check whether the synthesis fellow given the right netlist or right SDC, right? So for that, we need to go for check design. -R. So this is a command will give you entire information about the design. Before doing the backend, every process is very important in IC design, right? It takes too much of time, too much of cost. So to avoid the mismatches, we are just confirming the initial stage. So whether RTL fellow gave proper netlist or not. Is there any floating nets? Is there any multi-fan-out nets? Are you there? So such kind of verification we are doing in the initial stage. And also we are going for unified design. That unified design says, so the component, right, we should not use same component in different places. Each and every module need to have a different instant name, right? So everything we have to confirm in the initial stage, that is called check design -R. This will give you what is the approximate area, what is approximate power required, what is approximate timing required, right? Everything will come to know. Whenever you are finding a difficulty or any other issues, we need to say to the RTL fellow, saying that there is a bug in RTL, correct, and give me, right? So that fellow will take care of your RTL and you just do some optimization. Again, he will give you gate level Verilog netlist as well as SDC. Considering the modified .pgl.stc, we need to go for time design. That is also another check we have to go for time design. So this time design will give you 4 different information. So if you take any design, design is divided into 4 different parts. So this is your design, let me assume. So entire design is kept between reg to reg, and your entire design is broken into 4 different parts. That is, you have an in-outs, right? This is in 0, in 1, into some carry. Okay, I have a design. So your design is divided into input to reg path, that is into reg path, reg to reg path, that is register to register path, and register to output path, register to output path, and into out path. The moment you say time design, immediately the time design will invoke the timing engine. The timing engine will divide entire design into 4 different parts, that is into reg, reg to reg, reg to out, into out. Then it will apply the setup and hold predefined equations. It will just come out with the slack. Whenever you are having all these values into reg, reg to reg, reg to out, into out, right? All are positive. Then it says yes, there is no bug in the PG, gate level very long at list. If you have all your slacks as positive, it says you are good. There is no problem with the timing. So you are just confirming the high fan outs, multi-driven nets, right? And also what is the area required, power required, all initialization, right? We are doing in the initial stage after data preparation. So you are going for check design, you are going for time design. Once the slack is positive, it says that there is no timing failure. Once the functionality is okay, then you will get proper results, right? So everything is please confirm and go to the next process. That process is called floor plan. That process is called floor plan. So we went for check design as well as time design. So actually timing will be verified in 5 different stages. One is pre-place stage, then pre-CTS stage, then post-CTS stage, post-route stage, then post-SI stage. So we have to do timing verification in each and every stage. The moment you went for placement, immediately you have to check. If you are going for pre-CTS, each and every stage is having some addition and deletion of components. If one component is added, definitely there will be a timing issue. We need to confirm whether positive slack setup, there is no setup violation, there is no hold violation, right? So every stage is having some optimization, addition and deletion components. So we need to confirm. So timing we have to verify in 5 stages. The initial stage, you are, whatever you are doing time design, right? That stage is called pre-place stage of time design. Before placement of your components into the chip, we are verifying with gate level Verilog netlist. That is called pre-place time design. Okay. Okay. So now after confirming pre-place time design, so we are going for floor plan. So that stage is called floor plan. So assume you are just going for the new house. You have some additional stationaries like cart, right, bureau. So before placing all that items into your house, we need to visit the hall size, bedroom size, right? And we have to see where actually I can place my bureau, where actually I can place my cart, right? In the same way, we have some specified silicon, right? We have some specified silicon. And also we have some hard macros like RAM, ROM, PLL, right? Hard macros, and also soft macros of your block. So initially we need to decide how many analog blocks are there, how many digital blocks are there, where I need to place all my blocks. Okay. So that identification is very important. That identification is called floor plan. We are not placing. We are identifying the right place for the right component, right? That process is called what? Floor plan. Okay. So and also while placing the macros, right? Suppose I am just having PLL. This PLL is having 100 connections. 100 interconnections. This 100 interconnections speaks with X module. Then what I have to do is I need to keep this X very close to this PLL so that my interconnect delay will be less. Is it correct? So when I place this X very close to this PLL, if both this PLL and X speaks together, keep this module together so that your interconnect delay becomes less, the timing will be improved. Right? That is also one important step we have to take care. Then in the floor plan, right, simply we should not place our analog as well as digital according to our wish, right? If suppose I have a RAM, so that RAM is having some IOs. So suppose I have IOs here, this IOs connects with this RAM. Then I need to keep this RAM very close to this IOs. Right there. So based upon the interconnects are represented with spilines. When you touch the block, the tool will give you the interconnects associated with entire design. Check how many interconnects associated with IOs. According to that, just move your modules close to the interconnects. As far as that is as high as possible, as less as possible, right? You please reduce your interconnects, that is interconnect RC delay. Make sure that there is no timing violation in the later stage. Okay, so that is one important step. And also, suppose this is my analog block. I just want to place some memory very close to this fellow. We need to have certain distance between these macros and macros. So minimum say 5 micron. Right? So all these considerations we have to consider and we have to go for the floor plan. Assume, so you finished all your floor plan. That is, you identified the right locations for your components. Okay. So that is floor plan is over. So a lot of precautions are there, we have to consider and do the floor plan. The next one is called power plan. So you have total, say suppose 25k components, right? So for that 25k components, 25,000 components, what is the power required? So you are the engineer, you need to decide what is the power required for your chip, right? So suppose if you are going for 180 nanometer, so allowed VDD is what? 1.8 volt. Allowed VDD is 1.8 volt and this is VSS and this is VDD. If suppose 20k components are there in my chip, only VDD VSS ring is sufficient to distribute the power. Only one ring is sufficient to distribute the power. If I have 1 million components in my chip, then definitely this only VDD VSS ring is not sufficient to distribute the power, since the VDD, right, which reaches the middle component, say suppose I have 1 lakh component here, right? So from here to here there will be a drop, that drop is called IR drop. This drop, this 1.8 whatever is there will appear here as 1 volt or 1.1 volt, right? That is not sufficient to trigger your component. To address this issue, we have to run the stripes around the code. That is, so connecting with main VDD VSS, please run your stripes. VDD VSS, VDD VSS, VDD VSS. So based upon the complexity, you can go for only vertical. If complexity is too much, please introduce horizontal also. If whatever the component, 1 lakh component, right, instead of picking the VDD VSS from the major ring, these components can pick the VDD or probe the VDD in the neighboring stripes. So in that way, you can just reduce the IR drop so that all these components will get equivalent 8 or approximate plus or minus 10. Right? So this is called power plans. So idea is every individual component need to get 1.8 volts or less span. Tolerable limit VDD is required. So that we are achieving in the power plant stage. Okay. So that is power plant. Once floor plan is right place is identified, right power stripes as well as ring is identified, right? Once it is over, then go for place design. Then go for place design. Place design places all your components, standard cells, hard macros, everything into the chip. That is called real placement of standard cells as well as hard macros. You may purchase some components from some other vendors, right? So that components, everything you can integrate and you can make a chip, right? So in that case, everything is placed into the chip. That process is called place. So we have again two options in place design. One is time based, congestion based. So if you are very much interested with time, if you are very much interested with speed, right? You please opt time based placement. If you are very much interested with area, go for congestion based placement. Okay. So this process is called place design, placing all your standard cells, hard macros, everything into the chip. Once it is placed, again we need to go for time design. This stage is called as pre-CTS time design stage. That is, before clock tree synthesis, we need to confirm the timing. Since components are there in the silicon now, we need to go for timing. So that is, again we are just verifying reg to reg, into reg, all other paths and confirming that there is no negative slack in your design. Once pre-CTS, that is after place design, timing is okay, then you go for the process called clock tree synthesis. Right? So we have three types of routing in general. One is signal routing, other one is clock routing, and then power routing, right? This is one of the important routing in our design, that is clock tree synthesis. So this is a process, right, in which we are obtaining zero skew. We are trying to obtain zero skew. What is skew? Suppose I have a flop 0, I have a port here, and I have flop 99. So this port connects to flop 0 as well as flop 99. So definitely my clock arrival time of f of 0, clock arrival time of f of 9 may not be equal. Since from here to here I have interconnect, long interconnect. This long interconnect will give you more RC. This more RC will give you a difference in arrival time. So that difference in arrival time is called skew. We have to optimize this skew. We need to make sure that all your flops takes the clock at the same time. Right? Suppose this fellow takes 2 nanoseconds, this fellow takes 1 nanosecond. Either you introduce delay here, 1 nanosecond, or reduce this delay as 1 nanosecond. So that your clock reaches f of 0 and f of 9 at same time. So that process is called CTS. So in this process, we are just inserting two different important components, that is called clock buffers and clock inverters. This is the two important components we insert into the clock path. We are just playing with only clock path, not data path. Right? So only clock path is optimized with this addition of clock buffers and clock inverters, and skew is optimized. Once CTS is over, immediately there will be an addition of components. Sure, since we are adding 10K or 20K based upon the design size of flops, 20K of flops. Additional buffers and inverters. Once additional buffers and inverters are added, we will be having some timing issues. We need to confirm the timing. That timing is called post-CTS timing. After clock tree synthesis, after insertion of all your clock path elements, again go confirm that you are getting positive slack or not. So that verification is called post CTS. Okay, once timing is paka. Timing is paka after CTS. Then we need to go for the process called routing. Then the process called routing. Again, routing, we have two types of routing. One is global routing, other one is detailed routing. We have two types of routing. One is detailed, other one is global. What is global and what is detailed? This is global and this is detailed. So I have a block. I have X block here and Y block here. What is my optimized way of interconnecting this XY? Either in this way or in this way or in this way. Right? So identification of optimized way of routing is achieved at the global stage. According to the optimization, what we decide, right? So we are going for the routing. That routing is called detailed routing. So we have two types of routing. Initially, there will be algorithm. That algorithm will decide the optimized interconnects, right? Optimized routing paths. So based on that, the detailed router will just go and place three nets. One is signal nets, power nets, clock nets. All three nets are routed. Once it is routed, right, immediately we need to, in this stage only, the complete routing is finished. Okay. Once routing is achieved, then we go for again check setup and hold violations. This stage, the STA is called as post route STA. Post route static timing analysis. Right? Once setup and hold violations are not there, then send your design details to DRC LBS fellow. Send your design details to DRC LBS fellow. That DRC LBS fellow will just take some caliber kind of tools. He will confirm there is no DRC violation, there is no layout versus schematic violations, right? That nil violations. Once nil violations are there, then again this fellow sends the design into the signal integrity fellow. When you are working with less than 45, we need to cross this stage signal integrity. So we have a number of issues: crosstalk delay, electromigration, transmission effects, ringing, right? All these issues comes under signal integrity. So we need to confirm there is no crosstalk, there is no noise, there is no migration, hot electrons, kuch bhi nahi, right? Once signal integrity check is over, we need to go for STA. That STA is called post STA or post timing, post SI timing. So here in SI, to avoid antenna effects, we may insert some Zener diode, right? To avoid crosstalk, we may go for some shielding kind of stuff, right? After adding all these stuffs, we need to again confirm there is no setup and hold violation. That stage is called post SI timing verification. Once there is no post SI timing verification, generate tape out, send this tape out to fabrication like Taiwan Semiconductor Manufacturing or Chartered Semiconductor Manufacturing, CSM, whatever the fab you want. Okay. Thank you.